Geometry is crucial to architecture. Did you know even cities built in the Indus Valley civilization had roads laid out with perfect right angles? In about 500 BC, Pythagoras gathered a group of disciples to study the structure of triangles, and what they discovered is taught to high school students in their geometry even today. After the discussion on the history of geometry, it is time to discover about geometry in molecular structure. So what determines the shape and geometry of these molecules? Keep thinking. Well, all of you recognize a triangle, but what shape is this? Well, that is what we will be talking about in this episode. But before we come to that, there are some things you need to know. Today we are going to learn about the valence shell electron pair repulsion or VSEPR theory and the shapes and geometries formed on chemical bonding, and look at some questions on exam decoded. Now, that's a lot for us to learn today, but don't get worried on hearing these big words. The concepts are quite simple, so let's start with the concept of VSEPR theory. Do you know who proposed it? It was Sidgwick and Powell in 1940. The theory was based on the repulsive interactions of the bonding and non-bonding electron pairs in the valence shell of atoms. Take a look at this animation. You can see that the repulsive force is the least between two bond pairs. It is a little more between a lone pair and a bond pair, and it is the maximum between two lone pairs. Let me repeat this for you. You can see that the repulsion force is the least between two bond pairs. It is a little more between a lone pair and a bond pair, and it is the maximum between two lone pairs. But why do you think these repulsive forces are important and I am repeating them? These repulsive forces determine the shape and geometry of the molecules as is stated in the VSEPR theory. The VSEPR or the valence shell electron pair repulsion theory predicts the shapes of the molecules based on their least possible energy. According to the VSEPR theory, each molecule adopts a geometry or shape that allows for minimum repulsion between electron pairs by simply maximizing the distance between them. This results in the least possible energy structure. Remember, a single bond, a double bond, and a triple bond each represents only one region of electron density. Here we can see that the non-bonding electrons take more space than the bonding pair of electrons and force the bonding pairs closer. It is not only the force of repulsion that affects the geometry and the shape of the molecules, even the electronic configurations do. Do you know what the VSEPR theory is all about? Great! So let's take a look at the geometry and shapes of the few molecules and begin with how they are classified. Let's start with an everyday molecule like carbon dioxide. Also notice it has no non-bonding or lone pair electrons. So the maximum separation is possible only when the two regions representing the two double bonds are in a linear shape. For this reason, its geometry is similar to its shape. Beryllium chloride and mercury chloride are the other two examples of linear geometry and shape but have single bonds. That was interesting, right? Let's see some more examples. Have a look at boron trifluoride or BF3 molecule, which has three regions of electron density. Boron trifluoride is a colorless gas with a pungent odor. So, what do you think the structure should be for this? Now take a look. It has three bonding regions of electron density around the central boron atom, resulting in trigonal planar geometry and shape. As it has no non-bonding electrons, its geometry is the same as its shape. Understanding these structures is so interesting. Learning through examples is the best way to understand the concept well. So, let us look at another example. Next we have methane. Methane is also known as Mars gas and has a molecular formula of CH4. This molecule has four regions of electron density around the central carbon atom, as you can see here. What shape does it have? Can you guess? It has a tetrahedral geometry and structure. Notice the molecular geometry and shape remains the same here because there are no lone pair of electrons. Did you know even ammonia, a colorless flammable gas that is used in the production of nitric acid, fertilizers and explosives, has a tetrahedral molecular structure? But unlike methane, it has one pair of non-bonding electrons, which is why its bond angle is lesser by 2.5 degrees. Next we come to water. Water, which is an excellent solvent for ions and other polar molecules, is one of the few substances that decreases in density when it freezes. Taking a closer look at its structure, you will notice that it has two lone pairs of electrons. As lone pair repulsion is more than lone pair bond pair repulsion, which in turn is greater than bond pair repulsion, the bond angle of this molecule is the least amongst the ones we have discussed so far of the tetrahedral structure. Even though the water molecule has a tetrahedral geometry, it has a bent shape forming an angle of just 104.5 degrees. So, why don't you think about that the next time you take a sip of water?
In the tetrahedral configuration, one can see that the angle formed between the two bonding pairs of methane molecule is greater than the angle formed in the ammonia molecule, which is greater than the angle formed in the water molecule. A decrease in the angle from methane molecule to ammonia molecule to water molecule can be explained on the basis of the order of repulsion between electron pairs, which is greater for lone pair, followed by lone pair bond pair, and the least repulsion is seen for bond pair. In methane molecule, the bond angle observed is 109.5 degrees. If we look at the ammonia molecule, due to a greater repulsion between the lone pair and bond pair, the angle is seen to reduce to 107 degrees. which further decreases to 104.5 degrees in case of water due to greater repulsion between two lone pairs on oxygen.
I hope you have now started understanding various structures and geometries. To understand the next molecular geometry and shape better, let us take a look at PCl5 or phosphorus pentachloride molecule. This white crystalline solid has 5 regions of electron density around the central phosphorus atom. Now let us have a look at its molecular structure to get a better understanding. As you can see, it has no lone pair of electrons. So, there are 3 equilateral bonds at an angle of 120 degrees with 2 axial bonds. The geometry is trigonal bipyramidal. Another structure that we are going to study is that of sulfur tetrafluoride. Now this is a colorless and highly toxic gas which is very reactive in water. This gas molecule has 5 regions of electron density around the central sulfur atom, of which one region is occupied by a lone pair of electrons. These repel the 4 bonding regions . Another interesting example of a molecular structure having 5 regions of electron density is that of chlorine trifluoride. This is a highly toxic and colorless gas and has a sweet odor. It is extremely inflammable and can cause paper, cloth, glass, wood and even metals to burst into flames when they come into contact with this gas. Let us now take a look at its molecular structure. The central chlorine atom has 5 regions of electron density. 2 of these regions are occupied by lone pairs of electrons and 3 by shared pairs, giving it a T shape. All of us know xenon is a noble gas, but if excess of xenon is heated at 300 to 400 degrees, it reacts with fluorine atom to form ZeF2, xenon difluoride. So I guess the noble xenon is not that inert after all. The fluorine atoms are found in the axial positions relative to the central xenon atom. And the 3 lone pairs of electrons are found in a trigonal planar orientation at the equatorial positions around the xenon. For more such examples on 5 regions of electron density, log on to www.topperlearning.com. But before we move on to the 6th region of electron density, let us take a short break. In the meantime, why don't you think how many bonding regions and lone pairs are there in an amide ion? Keep thinking or wait till I return with the answer. So before I left, I asked you how many bonding regions and lone pairs are there in an amide ion. It is really quite simple. The amide ion has 2 bonding regions and 2 lone pairs. So with that out of the way, we move on to the 6 regions of electron density. Look at this table and notice how the presence of lone pairs affects the shape of the molecules and not their geometry. Those were a lot of examples, but hopefully they helped you visualize each kind of molecular geometry and shape. But if you are still confused, here is a short recap for you. The theory was based on the repulsive interactions of the bonding and non-bonding electron pairs in the valence shell of atoms. The lone pair repulsion is greater than lone pair bond pair repulsion, which is in turn greater than bond pair repulsion. An understanding of this helps in predicting the geometry and structure of a molecule. The VSEPR theory can also be used to predict the structures of molecules or ions that contain multiple bonds or unpaired electrons. But the theory is not foolproof and can fail in certain cases. Now that you are geared up with all these facts, let us waste no time and jump into some concept tests. Here is the first one for you. What is the geometry around the central atom in a PCl5 molecule? Is it linear, trigonal planar, tetrahedral, or trigonal bipyramidal? If you have been paying attention to today's episode, answering this question should not be a problem. Well, the right answer is trigonal bipyramidal. A PCl5 molecule has 5 regions of electron density around the central phosphorus atom. This means the central atom is connected to 5 other atoms and there are no lone pairs of electrons. The 3 chlorine atom in the equatorial region form a triangle. Add the 2 chlorines in the axial plane and you get a trigonal bipyramidal structure. Now that was a double revision for you. Question 2 coming your way. You will be answering this question based on the molecular structure of beryllium chloride. What is the total number of regions of high electron density around the central atom in beryllium chloride? Well, you know the answer. Yes, it is 2. Now, identify the most stable arrangement of the regions of high electron density. It is linear. Determine the shape of the beryllium chloride molecule. The beryllium chloride molecular shape is linear. Let's ask a few students a question now. How many regions of high electron density are around the central atom in SF2? The options are A, 2 lone pairs, 2 bond pairs. B, 3 bonding pairs. C, 2 bonding pairs. And D, 2 lone pairs.
I think so that the answer is A, 2 lone pairs and 2 bonding pairs.
The answer is D, 2 lone pairs.
The answer is C, 2 bonding pairs.
Well, some of you were correct. The answer is A. The SF2 molecule has 2 lone pairs and 2 bond pairs. Here comes the last one, just for you. How many regions of high electron density does anion have? Is it 3, 4, 5 or 6? Keep thinking during the break. I'll return with the answer and a few exam pointers and questions to prepare. Welcome back. I hope you did think of the answer for the question I had left you with. How many regions of high electron density does iron have? Is it 3, 4, 5 or 6? Well, if not, let me give you the answer. The triiodate anion has 5 regions of electron density. This topic is fun to do. I'm sure practicing a few more questions would only make it more enjoyable. Take a look. Here is a list of questions I have prepared for you on the basis of the CBSE course plan, and these are also important questions for the exam. The first one is, give the shapes and geometries of the following molecules: H2O, HgCl2 and SF6. The second one is for 1 mark. Tell me what is the geometry of HCN molecule. The third question is, give the Lewis structure, the total number of regions of high electron density and the most stable arrangement of the regions of high electron density and the geometry for ICl4-. All this for 2 marks. The next question is, draw the Lewis structure for CH3- for 1 mark. Draw the Lewis structure of amide anion. How many bonding regions and lone pairs are there in an amide anion? This one will fetch you 2 marks. That was a list of questions I would prepare if I was to give an exam on this topic. If you got these questions right, you automatically score full marks. You already have the right list of questions. Now you need the right answers to them. We have the right answers to 2 questions. Take a look. If you are asked for 1 mark to give the geometry of the HCN molecule, here is how you should structure your answer. Since there are no lone pairs around the central atom, the geometry of HCN is linear with a bond angle of 180 degrees. That was a perfect answer, and that will surely lend you that critical mark. So that brings us to the next question. If you are asked to give the Lewis structure, the total number of regions of high electron density and the geometry of iodine tetrachloride anion for 2 marks, this is how you should be answering the question. The Lewis structure of iodine tetrachloride anion is, here you can see that there are 6 regions of high electron density and the most stable arrangement is octahedral geometry. Now we are all set for our exams, but there are still some finishing tips left. For that, we have an expert to give you some important pointers.
I am here to give you some tips regarding geometrical shapes of molecules. First one, make sure you remember single bond, double bond, triple bond. Each represents only one region of electron density. The common molecular shapes is due to electron repulsion. Electron repulsions in high electron density cause them to arrange themselves in such a manner to minimize their repulsion. Second one, don't mislead by the term octahedral. In octahedral, many of the time you will get confused that there is 8 electron pair in central atom. That is wrong. Fact is that there is only 6 electron pair around central atom. The third point is, one of the way to represent electronic structure of the molecule is through models. Model is made up of toothpick and plasticine ball, where toothpick represents electron pair and plasticine ball represents central atom. The fourth and the last one is, you should practice Lewis structure thoroughly. That will help you in determining the geometrical shape of the molecule and ion correctly.
That is all for today, but do log on to www.topperlearning.com for more practice on the drawing of Lewis structure. I'll be back with another episode of Chemistry 11, but till then, keep thinking and keep learning.